Welcome to Math 31. This is a continuation of the lesson on applications of extrema, part 2. So I'll be covering the two remaining examples on your notes. And with this one, we just have a piece of wire, certain length, it's cut into two sections. And for whatever reasons, the one piece is bent to form a circle, and the other is bent to form a square. And we want to determine where should we cut the wire if we want the enclosed area, resulting area, to be as large as possible or as small as possible. So if this is the wire, and it's obviously a little wider than you might envision it to be, one part of it's going to be the circle, one part of it's going to be the square. Now you note that the domain in this case was from 0 to 8 inclusive. And a reminder that when you do have a closed interval and you're trying to come up with a max or a min, you don't need to do the interval analysis or second derivative test, because you can just compare the endpoints with the critical numbers and just select the largest or the smallest. Now, these questions are fairly lengthy, actually. And the best way to approach it is to, first off, call X to be the section that's going to be cut off to form the circle. So, or however you want to define it, it'll be the distance. You could put, obviously you could switch that around and you could have the circle on the right if you preferred, but I think you'll find this works better. And that would mean that 8 minus x, the total is 8 centimeters long, so that's going to be the amount that's cut off to be the square. So I'll indicate that at the top that x is the length to be cut off for the circle. Now the implications of that, because we're dealing with area, are that when we take a look at ultimately the circle, the area of the circle that we've got, you've got to recognize that x represents in addition to be the length to be cut off for the circle, this represents the circumference of the circle. And where I'm going with this, because I want to maximize the area or minimize, and in fact these questions are done just as one question, and we answer them both with our answers. But ultimately, we want to get the area, and so that means that I'm concerned principally with, as far as a circle goes, with the radius of it. The circumference won't actually enter into the picture directly, because circumference, of course, is a different measure than area. But what we can do is note that because the circumference is equal to 2 pi r, that the radius, if we did put the radius in terms of x, we would say that r is equal to x divided by 2 pi. And therefore, the area of the circle, which is pi r squared in general, is going to be equal to area is equal to pi. Instead of r, we would of course write that as x over 2 pi squared. So area is equal to, when we do go further with this one, it would be equal to x squared, and then the over 4 pi squared times on the denominator, then pi on the top. So when we simplify that, it'll give us 4 pi. So I'll do that directly. One of the pi's is going to cancel. And then when we turn our attention towards the square, because that distance is 8 minus x, and because this is a square, we also identify that the perimeter is going to be 8 minus x. And that being the case, each side, because it is a square, is going to be that 8 minus x divided by 4. And then for area for a square, it would be that side, 8 minus x over 4 squared. So now we have two formulas representing area of the circle and area of the square. Before I go on, I'm going to discuss the domain just briefly. I'm saying that the domain is inclusive 0 to 8, which would mean that it is possible that you could have x equals 0, meaning that it's all square, or you could have x equal 8, meaning it's all circle. And you're probably wondering, is that really right? And it is debatable. That's why I put it in there, so I didn't actually have to make a decision on it. In fact, for these questions, it matters, but it is the sort of thing that on your own you might say, well, really, if it's all square, then part of it isn't a circle. So it isn't really that clear unless you have the domain, and typically these ones will give you that for a domain. So it means that the total area which I'll write as a function of x, a at x, is equal to the area of the circle. So if you go back and take a look at that, that is x squared over 4 pi. Now I'm going to write that a little bit different because I'm going to eventually differentiate that. So I'm going to write that as 1 over 4 pi. So I have a fraction. It's much easier to differentiate. And then x squared, so 1 over 4 pi x squared, plus. Now the other thing that I want to do, which I didn't do earlier, in fact I should probably go back and take care of it, is our area of the square. Now this, to differentiate this, it will be easier if we take that denominator and square it out, which is 16. And then the area will be 1 over 16 multiplied by 8 minus x to the 2. That'll make our life a little bit easier. If we didn't do it, it's not a big deal, but we would just use the chain rule as per usual, and we'd be fine. In fact, you actually have other choices. You could divide the 4 right in if you thought that was going to make your life any easier. So now I have 1 over 16 times 8 minus x to the 2. And when we differentiate this one, a prime at x, with care, the 2 gets multiplied by 1 over 4 pi, so that's 2 over 4 pi. I'm going to reduce that right away to 1 over 2 pi x. And then the next one, well, 2 multiplied by 1/16 is 1 over 8. 2 over 16, 1 over 8. Multiplied by 8 minus x to the 1, multiplied by negative 1. And what we choose to do with the negative 1, well, we have choices. What I'm going to do, though, is just bring that to the front of that particular term. So 1 over 2 pi x, and this becomes minus 8 minus x over 8. And because I've differentiated it, I can leave it like that instead of putting the 1 over 8 in front. Again, though, it doesn't really matter. Now we have to make some sense of this, and what I've been doing, and you have choices, but you're looking for the critical numbers now. You could do what I did for the last few questions, which is when you set this to 0 to find these critical numbers, you could bring the 8 minus x over 8 to the other side to make it positive, and it works out just fine. So there really is no harm done when you solve it like that. I'm not going to, though. I'm going to get a common denominator, but just to keep sharp on that, but it really won't make much difference. It's just that this common denominator is quite easy because all we have is a 2 pi and an 8, so it's just 8 pi on the bottom. So that means the x gets multiplied by 4. So we get 4x, and then the second factor, 8 minus x, gets multiplied by pi. So I'll write that as minus pi times 8 minus x. So I repeat, this was just a decision that I made, but it's not going to make an awful lot of difference. Because when we set it to 0, we care only about the numerator. And this is basically where we'd have gone anyways. So 4x minus 8 pi, then plus pi x. And when distributing that pi in, now be careful with these two terms because these are actually x terms. So if we got them gathered up together, we could write this as 4x plus pi x. And remember, we want to solve for x. So now I'm going to bring that 8 pi to the other side. And then to get that x out, I factor it out, leaving me with 4 plus pi. So x is therefore equal to 8 pi divided by 4 plus pi. Now that's not a great number, but we were asked to get an exact value. And we've really done the main work. But what we have to do now is compare the endpoints and the critical numbers. And we've only got one critical number. To identify the min or the max. So our endpoints are 0, and then they're 8, and then also what we just got right here. Now, not surprisingly, this 8 pi over 4 plus pi is going to be the troublesome one. So I'll first off do the endpoint of x is equal to 0. And if you worked out a at 0, into the original expression, a at 0 is equal to 1 over 4 pi times 0 squared. So make sure you go into the equation before you differentiated it, plus 1 over 16 times 8 minus 0 squared. And then this is going to give you, well, that first term is 0, plus 64 over 16, well, that's 4. So a at 0 is equal to 4. So we file that away. And then we go for a at 8. And I'll do this on the same page because I think I can sneak that in. A at 8 is equal to 1 over 4 pi times 8 squared plus 1 over 16 times 8 minus 8 squared. Now, it shouldn't be too surprising that when you put those endpoints in, that one of the areas, either the circle or the square, will disappear. And so in this case, it's the square that disappears. Now, 8 squared is 64. 64 divided by 4 is 16. So check these numbers out, and then pi on the bottom, but that's what we're going to get. So a at 0 is 4. A at 8 is 16 over pi. And then I'm going to get some space, and I'm going to do the last one, which is the most awkward of the three. So now we have to find a at 8 pi. Oops. Try that again. A at 8 pi over 4 plus pi. We have a few ways to solve this one, and if you're lucky enough that it's going to be decimalized, then it's not a problem. But one of the difficulties with this problem is that we are supposed to get exact values. So I'm going to substitute in this into the expression. So it's 1 over 4 pi multiplied by 8 pi over 4 plus pi all squared plus 8 minus x. So this becomes 1 over 16 times 8 minus 8 pi over 4 plus pi all squared. And we got to work this one down. Now there's plenty of things you can do with this to make it work out well, but I think for this first expression it's hard to avoid having to expand that term, or at least the 8 pi. So that's going to be 64 pi squared over 4 plus pi squared. And I'm going to work this one down all the way, because that 64 over 4 is going to leave you with 16, and then 1 pi left on top. So 16 pi over 4 plus pi to the 2. Okay, so that's not too bad. And then the other one is going to be 8 minus 8 pi over 4 plus pi. Now, what you're probably going to want to do within that bracket is to get a common denominator, and then keep that 16 around. And let's see where this takes us. So the common denominator inside the bracket would be 4 plus pi, which means this minus 8 pi is unchanged. But you will have to multiply 8 by 4 plus pi. Excuse the writing being a little bit small there, to the 2. And then the factor of 1 over 16 in front. And then this will go down to 1 over 16. With care, we expand that, so that's 32 plus 8 pi minus 8 pi all over 4 plus pi. So it looks like we're going to get a break here. And then this to the 2, because your 8 pi's are going to go away. And I'm going to do this quickly, because 32 squared divided by 16 on the outside, so when you cancel that out, so 32 squared divided by 16 gives you a nice clean number of 64. So that's going to be 64 on top when we simplify that. And then the denominator, well, I'm still going to write that as 4 plus pi. I'm not going to expand it to the 2. And the reason for that is when we take a look at the other term, we see that we have 16 pi over 4 plus pi squared. So we've got the same denominator. And that's our a as a function of x equal to this. And then when you write this with that common denominator, we get 16 pi plus 64 over 4 plus pi to the 2. Factor out a 16, and you'll get pi plus 4 all over 4 plus pi to the 2. And then we get another break, because one of those pi plus 4's is going to cancel. So a as a function of x is, or in this case x is 8 pi over 4 plus pi. And then that's going to leave you with 16 over 4 plus pi. Now, to make sense of all of this, we have to compare these values. Which is going to be the max and which is going to be the minimum. So if you decimalize this, 16 divided by, open bracket, 4 plus pi, you'll get that this one's about equal to 2.24. And then if you go back to the previous page, which is what I'm going to do, and compare that, take a look at that 16 over pi, 16 divided by pi, this is about equal to 5.09. So now we can compare them. The a at 0 is equal to 4 is not the biggest nor the smallest, but the max is going to be 16 over pi, and the min is going to be the 16 over 4 plus pi. So to finish this, so this is going to be your min. And then to answer both questions, the area is maximized when a piece 16 over pi units or centimeters is oops. You see that number again? Oh, sorry. That's the answer. Excuse me here. 8 centimeters is used for the circle. So that would be how much goes for the circle. And the area is minimized when a piece 8 pi over 4 plus pi is used for the circle. So a lot of work for limited gain. But that's how you do those ones. Now one more to do, which is quite a bit less work. We want to find, oops, yeah, we've done this one. Get to the next one. Okay. Find the largest rectangle that can be inscribed in a circle of radius r. So here was what we have. So it's not a three-dimensional shape, just a circle, and we're putting a rectangle in it for whatever reasons. And there's no actual measure for the or numeric values for these. Now, if you take a closer look inside this, what we are trying to do is get the maximum size for the rectangle. And what I've got down below is based on what we have here for the original. Here's your radius right there. And we note to maximize a rectangle that we do use the formula L times W. Now I'm going to solve this one in terms of x. So I'm going to make the distance from the center of the rectangle right there to the outside, that's the inscribed part, to be x. So that's going to tell us information about the length and the width of this, or at least part of it. Because if you took a look at this remaining section, which is going to make up the skinny part of the rectangle, this, or the width if you like, that's going to be equal to r squared, using Pythagoras' theorem, minus x squared, but also the square root of that. So now we're able to solve this one in terms of r and x, because the length of this rectangle that we're going to place inside there is going to be 2x, since x is from the center to the end. And then the width is going to be, well, be careful with this one, because the width is, we have one section to be square root of r squared minus x squared, but we have two of those sections, so it's 2. And I'm going to write this in exponential form, so r squared minus x squared to the 1/2. So therefore the area is going to be equal to 2x, the length, times 2 multiplied by r squared minus x squared to the 1/2. So therefore the area is equal to 4x times r squared minus x squared to the 1/2. Before we get too carried away with this, we should note that the x value that we are working with would have to be greater than 0, could not be equal to 0, and it also has to be less than the radius. That would make sense even just from the position of the right triangle that we've got. R has to be larger than x. So let's keep that in mind. Now the thing of it is, when you're doing this problem right now, you're going to see that it's a little more complicated in some respects to differentiate, because it's going to involve the use of the product rule. So I'll say that u is equal to 4x. So u prime is equal to 4. V is equal to r squared minus x squared to the 1/2. So therefore v prime is equal to 1/2 multiplied by r squared minus x squared to the negative 1/2. And then we have to take the derivative of the inner part. Now the derivative of the inner part is the derivative of r squared. R is a constant, so it's going to be 0. And then negative x squared, of course, would be negative 2x, which makes life a little bit easier because it means v prime, 2x times 1/2 is going to go away on us. So we get negative x multiplied by r squared minus x squared to the negative 1/2. And now we use the product rule proper. The product rule goes like this, of course. Y prime is equal to u prime v plus u v prime. So I'm going to get a little space to do this. So y prime is equal to u prime, which is 4, and then multiplied by v, so that's r squared minus x squared to the 1/2. So it's a little bit of a concern that we've got an r there, but let's be patient with it. Hopefully it won't be a real problem. And then the next term is u, which is 4x, times v prime, which is negative x. So that means that we can make this sign negative. So I'm going to go fairly quickly to that point. It becomes a total of 4x squared. And then we've got the r squared minus x squared. And watch your signs with this one, because if you take a look back, the will be to the exponent of negative 1/2. So I think we're more or less set up. We will, as always with this sort of thing, have to look for take out a common factor, and I think in this case a 4 can be removed, as well as an r squared minus x squared to the negative 1/2. And that will leave you with r squared minus x squared to the exponent of 1. And then for the second one, the 4 is gone, so this is minus x squared is all we have left. So therefore, a prime as a function of x is equal to r squared minus 2x squared over top of the square root of r squared minus x squared. Now we also have a factor of 4 there, so don't lose that 4 in all the fuss. And then we look for the critical numbers. So they will occur where a prime at x is equal to 0, or where the function does not exist. But I'll start with this, 4 times r squared minus 2x squared. So this is where it's equal to 0. Divide the 4 out, and you're going to get 0 is equal to r squared minus 2x squared. Remember, you want the x value. So 2x squared is equal to r squared. So x squared is equal to r squared over 2. And when you take the square root, you'll get r over square root 2, or you could rationalize that. Now the thing of it is, I only took the positive root because the domain was between 0 and r, so it has to be positive. Now the other thing is, a prime at x doesn't exist. Well, this is a concern, but if you take a look at the denominator where r squared minus x squared is equal to 0, which is where that point would be, square both sides, you get r squared minus x squared is equal to 0. So r squared is equal to x squared. So you take the root, r will be equal to x. Or negative r be equal to negative x, but again outside the domain. And this is, in either case, it's either going to be negative, which is outside the domain, or it's going to be positive, which is outside the domain, because x must be less than r. So the only critical number is r over root 2. Now, the next step is for us to know what we would normally want to do with this is to set up the either do interval analysis or use the second derivative test to see whether or not this is going to work for us. Now, the thing is, in this case, I hate to do this to you all, but I'm going to not do the second derivative test with this, simply because this is going to be, at this point, more work and trouble than anything else. So a very important principle. So in this case, if you saw this on an exam, I would say don't bother with it, or use some other method, say graphing. So I hate to get lazy on you with this one, but this has been going on for a while, so I'm just going to say that it does the second derivative test. Will verify that this produces a max. Area. So check that one out if you want to get confirmation of it, and then answer the question. The largest rectangle. So the dimensions of rectangle. So if we have x is equal to r over root 2, it means the length is going to be 2 times r over root 2. So 2r over root 2. Now this can actually be simplified further if you wanted, but I'm going to keep it like that, just by simplifying the 2 and root 2 if you wanted to. And then the width, which we have to be the root of r squared minus x squared. So this would be the root of r squared minus x, which is equal to r over root 2 squared. So a lot of work for a silly little question like this. But that's r squared minus r squared over 2. So I'm just a little bit of space left to work with. That becomes the square root of, get a common denominator of 2. So 2r squared minus r squared, which would be the root of r squared over 2. And then we're going to get some shocking information. A little bit tight here, but when you take the root of r squared, that's r, and then we get root 2. So this means that the dimensions should be r over root 2 by r over root 2. So this means that it's going to be a square that's inscribed, which probably wouldn't surprise most of you anyways. So that's it for this one. That, in fact, will take care of all the applications, and then the next lesson we'll get on to some back into curve sketching. So thank you for your time.